Welcome to this explainer. Think about the last time you flew. You're cruising comfortably at 30,000 feet, sipping a coffee, totally relaxed. But literally just outside your window, hidden inside the metal structure, there's this incredible engineering feat happening every single second. We're talking about keeping a highly flammable liquid flowing safely, continuously, and perfectly pressurized in one of the harshest, coldest environments on Earth. This fuel isn't just some basic power source. It's the absolute, intricately managed lifeblood of the aircraft.
So, let's look at our flight path for today. We're going to cover the lifeblood of flight, inside the fuel tanks, the pumping and distribution, defeating ice and dirt, and finally, monitoring the system. Let's get right into it.
Starting with Section 1, the lifeblood of flight, anatomy of aviation fuel.
Now, we have to start right at the source, looking at fractional distillation. Notice how aviation fuel, stuff like Jet A or Jet B, sits perfectly in the middle of the distillation column. It's extracted at around 170 degrees Celsius, which makes it a kerosene-based fuel, totally different from regular aviation gasoline or what you put in your car. And why does that actually matter? Well, turbine engines operate in extreme freezing environments, but they also have to start reliably in midair. So this specific jet fuel strikes a perfect chemical balance. It's got low volatility to resist dangerous evaporation and vapor lock in the tanks, but it's still volatile enough to ignite under intense pressure when it really counts.
Think of this as the aircraft's cardiovascular system, and it has some really strict, uncompromising requirements. First, it absolutely must provide an uninterrupted, contaminant-free flow, no matter the gravity shifts or the aircraft's attitude. Because fuel is incredibly heavy, right? It makes up a massive portion of the plane's total weight, so the system has to handle wild weight shifts during steep climbs or dives without throwing the whole plane out of control. It also maintains precise flow and pressure, and crucially, it ensures absolute system independence. Basically, if one component fails, it can't disrupt the supply to another system. It's an entire architecture built on total redundancy.
Moving to Section 2, inside the fuel tanks, storing the lifeblood.
The sheer scale of the storage challenge here is just massive. Let's use the Boeing 777 as an example. The vast majority of its storage space is actually inside the wings themselves. Between the left, right, and center tanks, this single aircraft holds over 45,000 gallons of fuel. To put that into perspective, that's over 300,000 pounds of highly flammable liquid stored largely within the sealed wing structures right under your feet.
So how do they fit all that in there without making the plane too heavy to fly? Well, smaller or older planes might use bladder or rigid tanks. These are separate containers strapped or clipped into the airframe that you can pull out for maintenance. But large jet transports rely on what we call integral tanks. This means the actual structural skin of the wing itself is sealed with a special two-part compound to hold the fuel directly. By using the wing's own structural box as the tank, you get the absolute maximum volume of space, while keeping the weight as low as functionally possible.
But having that massive open space inside the wing creates a pretty terrifying physics problem. Imagine a sharp turn or a really aggressive climb. How do we stop tens of thousands of gallons of heavy fuel from violently sloshing away from the vital pumps that feed the engines?
The ingenious solution is the baffled check valve. These are essentially smart, one-way doors built right into the structural ribs of the wing. When the plane maneuvers, these valves easily let fuel flow inward toward the lowest point of the wing where the pumps live. But, and here's the clever part, they instantly snap shut to prevent that fuel from flowing outboard toward the wingtips. This guarantees that the vital boost pumps, sitting right at the bottom, always have a steady, deep pool of fuel to draw from, absolutely no matter the aircraft's attitude. Section 3, the pumping and distribution, the heart of the system.
Okay, before we can pump it to the engines, we have to get it into the plane efficiently. Smaller planes use manual over-the-wing refueling. Literally, you open a cap on top of the wing and pump it in. But modern transport jets use pressure refueling. This uses a single-point connection, usually accessible right under the wing. A ramp truck hooks up a high-pressure hose, and all the aircraft's tanks can be filled simultaneously from the bottom up. It even features an automatic shutoff system when the tanks are full. It's vastly more efficient and way safer for ground crews.
Once safely inside, the fuel's dynamic journey begins. First, a centrifugal boost pump acts as the heart of the system. Its spinning impeller draws fuel in through a protective screen and pushes it out under positive pressure. Next, it's pushed into a transfer or cross-feed manifold. This is a brilliant network of tubing that allows literally any tank to supply any engine if needed. Finally, the pressurized fuel flows through motor-operated engine shutoff valves, giving the pilots ultimate control, and then straight into the power plants.
But what goes in sometimes must come out before it ever reaches the engines. Mid-air fuel jettisoning becomes necessary if a plane has an emergency right after takeoff. At that point, it's likely way too heavy with fuel to land safely without destroying the landing gear, so the distribution system uses those exact same boost pumps to safely dump fuel overboard. However, strict safety rules dictate that the system can never dump everything. It's designed to automatically stop, reserving at least a half hour of maximum continuous power so the plane can still navigate and land safely.
On to Section 4, Defeating Ice and Dirt, the Immune System.
Just like a biological immune system, the fuel network relies on layered filtration defenses to survive. First up, coarse wire mesh strainers sit right at the tank outlets to trap large, dangerous debris. Further down the line, you have micronic cellulose filters. These are incredibly fine meshes blocking microscopic particles. We're talking 10 to 200 microns in size, roughly the width of a human hair. They even absorb suspended water. But here's a massive safety feature. If these filters ever get completely blocked by dirt or ice, a mechanical bypass valve automatically pops open, because delivering dirty fuel to an engine in midair is infinitely better than delivering no fuel at all.
Now, I mentioned those filters can trap water. But remember, at 30,000 feet, the outside air is well below freezing. Any water condensation that naturally occurs inside the tanks is going to quickly turn into solid ice crystals, which will instantly clog those fine filters. So how do we stop the fuel from freezing mid-flight?
The solution here is so elegant, it's the Fuel-Cooled Oil Cooler, or FCOC. It's essentially a mechanical heat exchanger. On one side, you have freezing cold fuel coming from the wings. On the other side, you have boiling hot lubricating oil coming from the working engine. By passing them right next to each other, the hot oil safely melts any ice in the fuel, warming it up perfectly for combustion. At the exact same time, the freezing fuel cools down the engine oil, keeping the engine from overheating. It's a highly efficient, 2-for-1 system.
Finally, Section 5, Monitoring the System, the Nervous System.
We established earlier that thousands of gallons of fuel are constantly sloshing around in these massive wing tanks during turbulence or steep maneuvers. So how do pilots actually get a perfectly steady, accurate reading of exactly how much fuel they have left? A simple mechanical float valve, like the one you have in your car's gas tank, would be bouncing all over the place, giving wildly inaccurate readings.
The answer is a sophisticated network of variable capacitance transmitters. Instead of a mechanical float, multiple electronic probes drop from the top to the bottom of the tank, and they measure the electrical capacitance of the fuel itself. These probes are wired together in parallel. So think about it, if the plane banks heavily and fuel sloshes to one side, one probe will read very low, but the probe on the exact opposite side will read very high. The system instantly averages these changes out to calculate a perfectly steady, incredibly accurate total fuel quantity, no matter what the plane is doing.
All of this critical data is routed right to the pilots, and the key cockpit indications aren't just about fuel quantity. The crew sees the mass fuel flow measured dynamically in pounds per hour, showing them exactly what the engines are burning. They monitor fuel temperature warnings to make sure the heaters are working. They even have filter bypass lights. Remember that mechanical bypass valve we talked about? If it pops open because of a clog, a light immediately warns the pilots, along with low-pressure lights if a boost pump ever fails. Everything is seamlessly processed into digital glass cockpit displays, keeping the crew fully informed.
But listen, aviation engineering never relies entirely on electricity. If the electronic digital indicators totally fail while the plane is on the ground, crews have a foolproof manual backup. They can physically walk under the wing and pull down a drip stick. As they carefully lower this calibrated stick from the bottom of the tank, fuel eventually enters a hole in the top of it and drips out the bottom. The ground crew notes the measurement, checks the manufacturer's chart, and can manually calculate the exact pounds or gallons of fuel physically sitting in the wing.
It's an astoundingly robust network of redundancies, constantly fighting gravity, pressure drops, freezing temperatures, and contamination. So the next time you glance out the window at that massive wing, you'll know exactly what kind of brilliantly engineered, heated, filtered, and continuously monitored cardiovascular system is keeping you safely airborne. Ask yourself just how much invisible engineering is constantly working, perfectly synchronized right under your feet to keep you flying. Thanks for joining me on this explainer, and as always, keep exploring.